So how does this decibel work? How do we convert from pressure in pascals to decibels? We use this equation. And it's really just a logarithmic ratio of two numbers. That's all a decibel is. And it isn't specific to acoustics or sound pressure. You can take any numbers and theoretically convert it into decibels. It's really just a logarithmic ratio. We use it for pressure because of those aforementioned aspects of human hearing. Okay, so we take pressure from our measurement microphone, we divide that by what we call our reference pressure, and we all need to agree what this reference pressure is. And then we take that ratio, take the log of that, multiply by 20. That's your sound pressure level in decibels. We're making a measured pressure up here. We divide that by a reference pressure, take the log of that ratio, multiply by 20, and that's our decibel. Now you notice in this equation, we're always talking about this pressure that we're measuring as an RMS quantity. So it's important to understand it's not a peak or a peak-to-peak value, it's an RMS. And the reference pressure we'll use in all of acoustics is 20 micropascals, or 20 times 10 to the negative 6 pascals. Okay, and we'll talk about where that reference pressure comes from, but this is how you convert pressure into decibels. Okay?
Looks pretty straightforward.
Yeah. So if we look at this conversion for decibels, we'll use decibels, and we call it sort of the original sound quality metric. Sound quality metrics are trying to make sound and the qualities of sound, like amplitude or frequency, more convenient for us to use for human beings. Decibel takes that awkward Pascal scale for human hearing and converts it to something much more convenient, and it sort of matches our perception. So that's why we use decibels. So if we look at this conversion and we take that reference pressure and we plug it into that equation, so now we're measuring 20 micropascals, we divide that by our reference, which happens to also be 20 micropascals. That ratio becomes 1. And Pete, do you remember the logarithm of 1? What is that?
That's a big naught. 0.
That's right, it's always 0. So when you register 0 dB on your sound pressure level meter, that means you are measuring your reference. Okay. Now if we jump up to much bigger number, 1 Pascal, nice easy round number, convert 1 Pascal into decibels using that same formula, we'll calculate 94 dB. Okay, this is often used for microphone calibration. It's a nice round number. 94 dB equals 1 Pascal, and so it's just a nice convenient unit. Now, something interesting is I'm going to show you here where I take 1 Pascal and I double that, and I go from 1 Pascal to 2 Pascals. I've doubled the pressure. What happens to my decibel value, Pete?
Yeah, 94 to 100 is a 6 dB
6
increase.
dB. Yep, so we went from 1 to 2, so an increase of 1 Pascal is 6 dB. But now what? Let me show you something weird. I'm going to double it again. I'm going to go from 2 all the way up to 4. So now my increase is twice as much as it was last time. Now how much does it go up?
100 to 106, 6 dB. So
6 dB.
Again, 6 dB.
Yes. So this is the price we have to pay for the nice convenient aspects of using decibels for human hearing. We have this awkwardness where you have to sort of take the good, take the bad, you take them both, and there you have the facts of the decibel. Where 6 dB is always a doubling in your root measurement. So no matter what, if I'm going from 2 Pascals to 4 Pascals or 100 Pascals to 200 Pascals, that increase will always just be 6 dB. Okay.
That's
so
crazy.
It's a little bit awkward. Yes,
it's
like,
very
awkward.
But I've reduced the sound of the product by 50%. The sound pressure's gone down, and it's went from 66 dB to 60.
Yes, and if he doesn't understand this aspect of decibels, you might be in some big trouble.
Yeah.
You'll find yourself talking in OOOs and nots.
Yeah.
Pretty
or
soon.
Put on a special list and can end up working for Siemens or something.
We all end up here sometime, don't we?
Yeah.
But let's talk about summing these values now. Okay, so this is an important thing. I've got multiple sources on my machine or whatever product I work on, and I need to reduce the sound level. Let's learn about how these things sum together. Let's say I've got 2 machines, they're running in my office simultaneously, and each of them makes 2 Pascals of sound pressure, or 100 dB. What am I going to calculate for an overall level with both machines running?
Probably like 200 dB. It's going to be pretty loud.
Well, we always work in the root unit, so we always sum the pascals first. So, we talked about 2 pascals plus 2 pascals is 4 pascals, right? If we just did a straight linear summation. So we might say a doubling of pascals should give us 6 dB, right?
Yeah.
Well, this is going to highlight an important aspect of summing sources in noise, is that we can't just take a straight sum. We have to do this RMS sum, okay, this root mean squared. So we have to take 2 squared plus 2 squared, so that's 4 plus 4, that's 8, and take the square root of that. And so the square root of 8 is 2.82. That's actually how many pascals we get when we sum them together.
Yeah, that makes sense.
And we're going to talk about why this phenomenon happens, but 100 dB plus 100 dB is actually 103 dB.
Wow.
Okay? Yeah.
I was a little bit off with 200 dB.
A little bit, but, you know, we've come to expect that. And it's just part of the magic of who you are, Pete.
Yeah, magic. I don't know if that's the right word.
So a 3 dB increase in adding together our 2 sound sources. So why does this happen? Well, we have this thing called coherent and incoherent sound sources. It makes a big difference. And coherence is just a fixed phase relationship. In my previous example, I had 2 random sound sources, so they're just playing noise in a random fashion. So there's can be no relationship between these 2 sources, and so they're incoherent. And so what's going to happen is sometimes these things are going to be acting together and they're going to sum together, and sometimes they're going to be acting opposite and they're going to cancel, okay? And so if we look at these 2 sine waves with a real simple example, each of the
These
sine
are
waves
like the 2 sources and the pressure fluctuations coming out of them?
Yes, so we're measuring source number 1 in the red, and you see it's about 2 pascals of a sine wave of a pressure oscillating back and forth. The second sound source, also 2 pascals, it's shown in green here. But you notice that they're at slightly different frequencies, and so sometimes they are adding together. Like right here, they're both pointing down, so they're going to sort of constructively interfere with each other, and we're going to get 2 plus 2, and you see the magnitude is now like close to 4 down here. So they're in phase, and the signals add together. But a short while later, a couple cycles later, now they're completely out of phase. The green is going up, red's coming down. Those cancel out, and we essentially get 0.
Wow.
Okay, and so we go from 4 to 0, and we're going to kind of bounce back and forth between those 2 numbers, and that's why we can't just sum 2 pascals plus 2 pascals, because sometimes it's 0 and sometimes it's 4, and so that's why we use the RMS sum when we're summing sound sources.
So we won't be quite as tall as the highest blue peak, and we won't be 0 either. The RMS is somewhere in between.
Yep, exactly. So we got to keep this in mind when we're summing sound sources, okay? So now let's move on to a little bit more complicated example, where now I have 3 sound sources, and they're all at different levels, okay? So sound source number 1 is 10 pascals or 113 dB. Sound source number 2, 2 pascals at 100 dB. Sound source number 3, also 2 pascals, 100 dB. What do you think I'm going to get if I sum source 1 plus 2 plus 3? I've got them all running at the same time. Well,
luckily the answer is there on the slide.
Right, it is. And it's 114.3 dB. Again, we're going to do this RMS sum. So 10 plus 2 plus 2, that gives us 10.3. Convert that to decibels, 114.3.
That's 10 squared plus 2 squared plus 2 squared, all square rooted, 10.3.
Correct. Yep, exactly. What do you notice about this sum, 114.3?
That 114.3 is very close to source 1.
That's right. When I'm working with Pete, I like to put the answers in big boxes right from the start so he doesn't get too lost.
I appreciate that. Always.
But he got it right this time. Well, I'm here for you, man.
Well, you know, I do have trouble reading what's in front of me.
Well, that's because you're so far ahead of everybody else that you often miss the most obvious. But yeah, Pete's right. Sum is almost identical to the largest source. Source number 1 is 113. We add 2 100 dB sources on top of that 113, and we really only get to 114.3, okay? So 113 plus 100 plus 100 is 114.3, okay? Again, we've got to do this RMS sum, but we see that largest source dominates, okay?